So yeah, as Sean mentioned, talking a bit diagonal Ramsey numbers and sort of recent results that I have on better upper bounds for diagonal Ramsey numbers via certain effective quasi-randomness techniques. Okay, so I'll with a short introduction about the history of this problem, and then talk a bit about a certain quasi-randomness and induction framework, which sort of underlines the best approaches to getting for diagonal Ramsey that people have discovered so far. And then I'll talk a bit about this quasi-randomness part of this quasi-randomness in the framework, and then talk about a couple ways in which the new results I have on effective randomness bounds, in particular as applied to this diagonal problem, a certain type of optimality and represented natural barrier. Okay, so just for some basic history, okay, so just recall the definition of a number is the minimum n such that every n vertex graph either has a clique of size k or an independent set of size k. So I'll denote an independent set by this bar k sub l. And Ramsey showed that they're finite on the order of a tutorial or something, and this was introduced in relation to logic. So the bound that you might be familiar with is the bound due to Arian-Szekeres, which is that R k plus 1 and L plus 1 most k plus L choose k. So this is a very classic upper bound. We'll revisit this in a moment. Now, as for better bounds, one sort of improvement that was found was due to Rowe in the 80s, and this is as far as I know unpublished. And basically it offers some small power of log improvement over this upper bound uniformly for all k and l. Although this is unpublished, I believe a weaker version of this, which saves maybe a log is published due to Rodel in Surveys and Combinatorics or something of the sort. Okay, but the techniques used very related to the techniques that we're going to be discussing today. So sort of landmark result, especially of the diagonal number, this result due to Thomason in 1988, where he shows that R k plus 1 L plus 1 is at most k plus L choose k times this prefactor. And so you can see here when L is around the same size as k, let's say L equals k, this is saving around 1 over root k over the well-known upper bound of choose k. So this you can sort of think of is sort of a minor improvement because 2k choose k is already 4 to the k over root k, so it's another root k. But already this is a pretty involved here. And he sort of establishes a framework that we're going to be building on today, and that was built on by David Conlon, who was able to use these techniques in a very clever way and show that R k plus 1 L plus 1, say when L and k are around the same size, now not only is maybe a root k improvement, but actually the super polynomial improvement. So explicitly, if L, say L over k is between epsilon and 1, and L is sufficiently large, then R k plus 1 L plus 1 is at most k to the negative c log k over log k times this k plus L choose k, this Arian-Szekeres upper bound. And so another way you could write this is e to the negative log squared k over log k. So now for the result that I'll be presenting about today. So what I show is something similar in a certain way, although this time, okay, so again, L and k are around the same size, L is sufficiently large. And now we have this upper bound on R k plus 1 L plus 1 with this improvement of e to the negative log squared of k. So you can see that this log k has been removed. And so for one, that is an asymptotic improvement, at least in this second order on the 4 to the term. But beyond that, and hopefully I'll get to explain what's going on, but beyond that, this in some sense represents a barrier to improvement with this quasi-randomness frame. Okay, so just the obvious corollary of this is that R k plus 1 is at most negative c log squared k times k choose k. Okay. So now let's just talk, step back and talk just a bit the Ramsey problem in general. So I would be remiss if I don't talk at least a bit about this lower bound. So as mentioned, the result that I have shows this upper bound of 4 to the k times e to the negative c log squared k. And there's a well-known lower bound. So here, this is the best known lower bound, which is around k over e times 2 to the k plus 1 over 2. So as mentioned, the best upper bounds are coming from this framework, which was introduced by Thomason and extended by Conlon and further extended by myself. And the and just to comment on this lower bound, if you sample from a GN1/2, famous argumented Erdős probabilistic method, you get this lower bound, but divided by a factor of 2. And this improvement of a factor of 2 over that union bound is due to the Lovász local lemma. So we won't talk much else about this lower bound or about other Ramsey problems and Ramsey variants, such as the regime where L is fixed, for example. We'll focus on the regime where K and L are roughly the same size. Okay, so the best upper bounds are coming from this framework of Thomason. And the improvement that we're getting in this secondary exponent is originating in certain optimal, what I like to call effective quasi-randomness results. And I'll just say a bit more about what the new ideas are here, even though maybe it won't make sense as of yet. It will require some technical to get into that, but it sort of derives from looking more closely and understanding the global structure of certain signed or graphon densities, rather than just a local structure, as what Conlon does, or with Thomason, it's more of a restricted thing. And so maybe we'll see more of this as we go forward. Okay. And perhaps one thing to highlight, optimality, in a certain sense, demonstrates that this is a natural barrier, certainly to this framework for attacking the Ramsey problem. There are a couple of ways you could think of, hopefully we'll get a chance to see, to try to overcome this barrier, but there is something legitimate here. Okay. So let's talk a bit about the Thomason framework of quasi-randomness and induction. So the starting off point is really this Erdős-Szekeres upper bound. So probably a lot of you have seen this argument, but I'll just repeat it here, be using various arguments. So they show k plus 1 L upper bounded by RK L plus 1, RK plus 1 L. And along with some base cases, this immediately implies the desired result because binomial coefficients are nice. And okay, the way you do this is you basically look at a vertex and you know that a graph doesn't have a k plus 1 clique or an L plus independent set. It doesn't have too many neighbors. It doesn't have too many non-neighbors. And that really gives a bound on the graph size. We'll go through this argument in some amount of detail. We'll actually rederive it. And also more as we talk about this topic. So instead of this bound k plus L choose k, which Erdős and Szekeres basically inductively prove, Thomason is going to inductively demonstrate a bound of the form RK plus 1 L plus 1 is at most alpha of k L times k plus L choose k. The hope is that you can take alpha to not just be the constant function 1, which would be this error, but hopefully you could take alpha to be some decaying function of k and L, or at least some function that decays in the ranges that we care about. And that'll give the win. And in Thomason's case, he wants to take it to be around 1 over root k when k and L are approximately the same size. So, okay, so throughout some of the arguments that'll follow, we're implicit induction. So if we're talking about the Ramsey problem for k plus 1 and L plus 1, we're sort of implicitly assuming that for smaller values, we already have this bound potentially. Okay. A couple of definitions to allow us to talk about these things. So I'll be calling a KL Ramsey, or just Ramsey when it's clear. It has no clique of size k plus 1 and no independent set of size L plus 1. And we're going to be focusing on graphs that have this size of the bound that we care about. So we're going to let n be the floor of alpha kl times k plus l choose k, and let alpha star be n over k plus l choose k. So this alpha star is deal with this round error that might occur because alpha times k plus l choose k is not necessarily an integer. And the name of the game is to basically assume that we have a graph on n vertices, which is quite large, and say something meaningful about it if it has the k. And in particular, the goal would be to eventually derive a contradiction, say at this value of n, and that would show the desired Ramsey number upper bound. So let's just hop right in. So recall these notations. So what did we do, or Erdős and Sekeres, what did they do for their art? What they essentially viewed is any vertex, it has only so many neighbors or so many non-neighbors. The idea that Thomason has is to extend this a little bit in the following way. So I have a KL Ramsey graph, then it has the following properties. For one, suppose I have a clique of size R, and then I want to find a vertex that extends it to a clique of size R plus 1. How many ways, how many possible such vertices can we find? So if you think about it, the answer is at most this number, r k plus 1 minus r, comma l plus 1, and then minus 1. The reason is, okay, and there's something similar for independent sets. And here's perhaps a pictorial reason that'll help visualize this argument. So on the left-hand side, we have this, say, a group of r vertices. I guess in this case, r is 3. And suppose they're all connected in the graph, these orange edges. We're assuming they're connected. And we want to know how many vertices complete it into a K4. So here we have pictured this group of vertices that complete this K3 into a K4. Suppose we have, in this case, we have at least 5 of them. Now the point is, supposing that I had r k plus 1 minus r, comma l plus 1 vertices, so this number plus 1, if I had that many vertices in this group, either I could find an independent set of size l plus 1, which would violate the KL Ramsey property graph, or I could find a clique of size k plus 1 minus r inside of this neighborhood, sort of this common neighborhood. I also have r vertices on this left side, and they're fully connected. So all told, all put together, that gives me a clique of size k plus 1. And so that would also contradict the Ramsey property. So this sort of simple argument, which you can think of as restricting to the Erdős-Sekeres argument in the case r equals 1, gives you this result. So as a concrete example, when r equals 1, a k1, which is a single point, extends to a k2, which is an edge in at most so many ways. That is, you have a bound on its degree. And similarly, a k1 bar, which is also a single point, extends to a k2 bar, which is a non-edge in at most some number of ways. And those are precisely the degree bounds that you get from the Erdős-Sekeres argument. Okay, yeah, so more explicitly, within this framework of induction that Thomason sets up, for any vertex using this r equals 1 property, we have its degree, which I'll denote by dv, it's at most this value. And by this inductive hypothesis that we're assuming, we know that this Ramsey number is upper bounded by its corresponding alpha times k plus l minus 1, choose k minus 1. And if we just work out what that equals using what we know about n and alpha star, we can see that it equals this value, or is upper bounded, strictly upper bounded by this value. So you can sort of see it's less than k over k plus l times n, maybe times something. And since alpha is decaying, this something here is going to be slightly bigger than 1. So there's a little bit of room compared to when alpha equals 1, the Erdős-Sekeres argument, it would just be strictly less than k over k plus l times n. And similarly, using this we get something similar for its sort of the complement of its degree. So we get this upper bound. And okay, we can similarly use the inductive hypothesis, and if we do some calculations similar to before and put it all together, we get the following bounds. So we find that the degree over n is between these two quantities, which are sort of symmetric to each other in a certain sense. And perhaps one thing to note off the bat is that if alpha is the constant function 1, then you can see that actually alpha star is also 1. And this bound over here will say that the degree divided by n of a vertex is between k over k plus l on the left-hand side and strictly less than k over k plus l on the right-hand side, which is an immediate contradiction. And so this actually already proves the Erdős-Szekers bound when alpha is the constant function 1. So this is sort of a generalized framework that allows you to incorporate this argument, giving this k bound. It also has additional properties on this graph, which will prove useful. Okay. So now the question is, if alpha is decaying, then instead of being sort of sandwiched at k plus l, there's a bit of room. And the idea is, how do we get a contradiction in that case? And so now you can sort of imagine why quasi-randomness is going to show up. So just to recall the degree bound that we had, it'll be convenient to let p equals k over k plus l. So this property is going to tell you, as long as alpha is sufficiently slowly decaying, that our Ramsey graph has degrees that are approximately p times n. So one nice consequence is that since we know all of the degrees to a good degree or a good amount of precision, we actually can control certain counts. So in particular, we can control the number of triangles plus the number of complete, I guess, independent size 3, like non-triangles, relatively well. And the reason is, if you double count over triples of vertices in 2 different ways, you can actually show the following formula, which basically allows you to control the sum of triangle count and the independent set size 3 count in terms of the degree sequence. So this is sometimes called Goodman's formula. And we know what all of the degrees are approximately. They're all near p times n. So this right-hand side over here, we almost completely control. And what this value is going to end up being, if you actually plug it in, I'm not going to do it here, but it's going to be basically the number that you'd expect if our Ramsey graph was quasi-random. That'll be approximately what the triangle, sort of the triangle plus complement triangle count that you get will be. So on the right-hand side, using the bounds that we already have on the degrees, we can pin down what this value should be. But on the other, we can actually give an bound to this left-hand side by computing it sort of in a different way. So here's where we're going to recall 2 key properties. Not only does every k1 extend to a k2 in certain, but now we're going to use the r equals 2 of this line we had earlier. And so here's a restatement. Every k2 is going to extend to a k3 in at most so many ways, and similarly for a k2 bar. And again, by induction, we know bounds on these values based in terms of alpha. And okay, so I'm not going to actually do it out as it's somewhat of a explicit computation, but since we also have a bound on how many k2s there are in a graph, and then we know how many times a k2 extends into a k3, or an upper bound on such, and similar for k2 bars, you can just put it all together and you can actually determine an upper bound on this left-hand side. And it turns out if alpha is sufficiently slowly decaying, such as the bound that Thomason wants to get, you immediately get a contradiction. So I'll maybe leave that as sort of dies, just because it's somewhat of a technical computation. Okay, so that concludes our discussion of how Thomason is getting this one. And you can see he essentially only has to use this clique, as you might call it, for r equals 1 and r equals 2. So the way in which Conlon extends Thomason's framework is to use higher values of r. Now, there's no analog of this Goodman's formula. There's no analog of this formula here. But the idea is, okay, so we know that all of the degrees are close to like p times n. If we actually knew that this graph was quasi-random, then it doesn't matter that we don't have an exact formula in terms of the degree sequence, because we could still say that the clique counts and the non-clique counts are close to what they should be in a quasi-random graph. And maybe that along with this clique bound giving an upper bound on the number of cliques, maybe those two together will give us enough on its own. And it turns out that that is basically good enough. So as I mentioned, there's no analog of this formula, but what you can do is using this Ramsey graph, you first have to show it's quasi-random in a certain sense. And then you can basically just compute the KR density or show it's very close to what it would be in a quasi-random graph. So this is sort of, if you're familiar with dense graph limit theory, this is sort of a standard thing in this area where you, for example, if you know that certain graphs are close to a cut norm, or if C4 counts are close to what they would be in a quasi-random graph, then you can get a counting lemma, and you know that all of the counts are correct in a certain sense. Okay, so I'm not going to go through exactly how you show that a Ramsey graph is quasi-random. I'm similar to before. You can show that a Ramsey, given a certain function, you can show that a Ramsey graph has its degrees in some range nearby to Pn. So let's just say that they're all in Pn minus mu plus n, where mu is what choice of alpha we take. And you can also show that for every pair of vertices, their co-degree, so the amount of vertex connected both of them, is upper bounded by, say, around p squared n plus nu times n, where again, nu and mu are both depend on the and maybe where this co-degree thing is derived, you can do this using the REQ version of clique extension property. To be a little careful. There are some technicals that you have to think about, but I'm not going to talk more about that. So as it turns out, maybe this expression looks somewhat familiar, but maybe it does sometimes. But as it turns out, if alpha of x comma y, so this is alpha k, is around the e to the negative r y or x log x plus y, then it turns out that mu and nu are both approximately r over k. They can value. And so Thomason's argument is basically the case where r is clear. And Conlon's argument, and what I do as well, will allow us to use a larger r depending on. Supposing for some value r alpha, supposing that we can show a contradiction, supposing that we can say, okay, Ramsey graph, using this function alpha, not only do we have a Ramsey graph, but we have a Ramsey graph has its degrees that are pretty regular and its co-degrees that are pretty regular, or at least upper bound, certainly, with this quality. If in that graph we can find a contradiction to the property, then, so there are some details and there are some technical considerations that I'm going to gloss over, but it's basically going to you have a bound for the diagonal Ramsey numbers on an upper bound of the quality e to the negative r log k times this 2k choose k behavior. And as similarly, this Thomason argument, maybe I'll actually go back and this Thomason argument where we show that the cliques and sets of size 3 is to be in the quasi-random graph or in this pseudo-random graph, and then also use the extension property to show an operand on the number of cliques. You actually do similar in this case. And for this value alpha, it turns out that the clique size to count is basically k sub r, 100r or something like that. So it's going to sort of abusive use the same r in both settings. And so the question that we really want to answer, and we can answer using this extension property, we can find this contradiction similar to Thomason's argument, although I'll go through these, but simulation essentially goes down to, in a Ramsey graph, do we have the total number of cliques, I guess, multiplied by 3 factor in this case, is around what it would be if it was a p quasi-random graph. So I'll just let sort of marinate for a second and say some words. So there are lies here beyond the ones I've already pointed out. So one lie, you don't actually exactly this equation exactly. You actually want to keep some of the lower order terms. Throwing them away actually sort of worsens the bound slightly. So that's more of a technical thing, but that's just a comment that's worth noting. Secondly, in this question, we've sort of reduced to the point at which sort of, we don't need to use the Ramsey property as strongly anymore. That matters. I mean, in order to have these clique counts be correct, really the thing is this this quasi-randomness. So knowing that these are bounded and knowing that these degrees are close to p, you can actually see pretty easily from this that the C4 counts are what they should be, basically. Even though we only have an upper bound on these co-degrees, since we have a lower bound on these degrees, it all works out. But actually, the quasi-randomness get C4 counts, and the bound that you get there is actually not quite strong enough, and you actually get a loss if you try to just work directly from the C4 counts and the quality you have. So it's actually necessary to keep these degree and co-degree conditions and use those instead strongly. And one sort of reasoning and justification for that is that in this regime, we care about counting cliques where R is going to be growing with K. And growing compared to potentially the quality of our quantiveness. So this is sort of why I'm calling this an effective quantiveness framework, because we really do care about the dependencies here. And for that reason, you do have to be a little careful with the sorts of things that you're doing. And as it turns out, when we have these quality of bound, in some sense, I have certain optimal threshold question. Okay, so I'm going to move on now. So this is sort of the setup, and this is sort of the framework for the rest of what I'm going to talk about today. Basically, if we can count cliques up to size R in a Ramsey graph, or basically a quasi-random graph, then we can get a bound on the Ramsey numbers. And here you can sort of see already what these R values are going to be. So for Conlon's result, he says, yes, we can do this as long as R is not bigger than log K over log K or so, some explosive constant times this. And that gives the bound that he has. And sort of I can remove this log, and as we've talked about many times already, there's a certain sense in which so there's a sort of a witnessing graphon that has the desired quasi-randomness bounds for the clique are far from what they should be. And hopefully we'll get a chance to get to that point where I can talk about that in more detail. Okay. I'll leave this for a second. So now we're going to sort of progress to the second part. So it's going to be more technical in nature. And we're going to recall some notions from dense graph limit theory and the notion of graphons and graph densities, etc. So here I'm going to maybe delve a bit more into the argument of the key ideas that go into these effective quasi-randomness results and answer to this question, basically. Okay. So just some preliminary definitions that should hopefully be clear to you. So a graphon is a bounded symmetrical function. Usually it's from 0, 1 to 0, 1. Here I've just allowed a bit more leeway just to, because we're going to want to care about signed graphons, and there are other technicalities that really they're stating very precisely. But for a function and for a graph, there is an associated h density. So this is denoted by t sub h of W, and I guess the definition over here, it's this integral over v of h different variables of w of xu comma xv multiplied over all of these variables. And so you can, for example, for those who aren't familiar with this notation, you could sort of encoding the adjacency matrix of a graph. And then in this sort of integral is really just a sum over indicator functions. And you get a contribution if and only if this pool of vertices is witnessing a subgroup. And so you see how, in some sense, this quantity is a natural notion. And there are a bunch of other nice properties from dense graph lambda theory that I won't talk about in too much detail. One other notation that might be slightly non-standard that will be convenient related to this is the following codegree. So given our values, x1 through xr, we define the codegree to be the expectation over y, or the integral of y if you want, of this product of w xi comma y over all. And again, if you're thinking about adjacency matrix, it's really a codegree in a certain sense, because I'm looking at the rows corresponding to the vertices x1 up to xr, and I'm at if and only if I have some value of vertex, which is essentially a neighbor to all of these guys, all of these people. And okay, so this is really a codegree. Okay. And now just set up a couple of the measures of quasi-randomness. These are basically going to encapsulate the notions of quasi-randomness that we already know about our Ramsey graph. So it should look somewhat familiar. So, okay, so given an arbitrary graph G, and so we'll really care about G being our Ramsey graph, we let WG be a function that is defined on the following basis. So it has underlying set the vertices of the graph, and it has the uniform measure on it. And we just let it be essentially this adjacency matrix. It be 1 when we have an edge and 0 otherwise. So this is sort of why I wanted to have a little generality, just because it's actually more convenient to embed graphs into this measure space. Rather, it's more canonical in a certain sense rather than adding it into 0, 1. We've seen that construction before. And we're going to care about the discrepancy of this graphon from a quasi-random graphon, which is just the constant function p. So we'll let fpg, or just f sometimes, be wg minus p. So this is sort of a signed version of these discrepancies from quasi-random. And finally, we define the following two measures of how quasi-random this G is. So the first we'll call mu, in keeping with what we were discussing earlier, and it's equal to this maximum, the maximum sort of quote unquote degree of f in a certain sense. And since f is measuring the distance between G and P, is really just saying what is the maximum distance of a degree of the graph from P. So normalized degree, really. So this is basically the mu that we had earlier. Be bounded by the mu that we had earlier. And mu sub P comma G is okay. It's something okay. It's basically how big can the code be compared to what is expected. Although it's not quite that either for a couple technical reasons, but you can sort of just think of it as measuring how far the code degree is from what it should be. There are a couple of technicalities because we only had an upper bound on the code originally. So this is actually sort of a one-sided measurement of the distance from quasi-random graphs, but that won't ultimately be too important. So you can just think of mu as just being the maximum magnitude of a code degree of f. And vertices just in order to make it make sense. Okay. And it turns out that nu is really the important quantity, just because code degree control quasi-randomness. So mu is actually important, but it's more for technical reasons that I don't want to get into. So I'll just focus on nu. And the key point with these measures of randomness have the K2A density. So think of this as a fully connected bipartite graph between two vertices and A vertices. And you can write it like so. You can write it as sort of the 8th moment of these code degrees. Since we know that the code degrees are essentially bounded by nu, this expectation and therefore this density is bounded by to the power A and then plus 1 over n, just because when x equals y, you don't have any control. So you just by, say, 1 or something. Okay, so this is true again because this is a 1 on nu. So this would be true if nu was an absolute value here. But since it isn't, there's 2 when it is an even number, but that you can resolve this. So I don't really want to focus on that. Sort of the key point is that this graph density that we have is quite small if we know that our original is pseudo-random. And the signed graph density, you can sort of think of measuring the level of discrepancy between our graph G and quasi-random graph. So this will be important. Okay. So now let's talk a bit about these actual effective quasi-randomness results. So remember that our ultimate goal was to, in a Ramsey graph, compute its KR density. And we were going to do that using these quasi-randomness properties. So, okay, so here, suppose H is some graph with R vertices. For example, the case that we really care about is this clique of summer. But this does work more generally. G is, say, our Ramsey graph. Let F be this graphon, which is the deviation from our G's quasi-random. So what we ultimately want to show is that this graph density, this H of G, is approximately P to the of the number of edges of H. So what we can do is we can look at this quantity on this left-hand side and expect that it's close to 1. We will be close to 1. And again, there are lots of technicalities, but that basically allows us to deduce a bound on the range, if we can do this for Ramsey. What we can do, we can write out what this graph density is. It's an expectation. And it's an expectation over a product over different values of W. And then I guess we have this factor here. So it's really a product over U of XY divided by P. And just remembering that W is P plus, we get the following form. So you can think of this as sort of encoding the concept that this 1 here is basically the term in our random, hopefully quasi-random graph. And these F terms here are sort of the deviation terms. And so we're ultimately going to want to control the deviation terms in a meaningful way in order to get a result. So what we do is we expand out this product and we compute the expectation of every term individually. So what's going to happen? If I chose for these edges of H, suppose I chose this term P inverse F. And for the terms, imagine that we chose the constant function 1. Then when you expand it all out, you're going to get the expression P inverse F. It is just P inverse times the K2 density of F. And you can imagine similar, choose, say, 3 different copies of F, and they're arranged in a triangle graph H, then I'll get a triangle density out, and so on and so forth. And so when you do at the combinatorics, what you get is you get the following. You get P to the negative E of J, CJH times TJ of F, where TJ is this graph density. And you're taking a sum over all possible isomorphism classes of graphs, J, that, okay, maybe it has no isolated vertices. Your CJH is the number of subgraphs of H that's perfect to J. So with this edge density, J equals K2, this just be a factor of E of H. And if I want to out, there are each different ways in which I find out this product. And similarly for every possible sort of structure of different Fs that I'm multiplying together. And it's worth noting that this sum includes the empty graph. And we're sort of assuming that the empty graph is 1 side of H. So the term corresponding to the empty graph is actually the main that we care about. It comes out to 1. And every other term, every other T sub J of F, you can think of as a Conlon density, which is sort of measuring the distance from our graph at random And maybe I'll backtrack just a little bit. Remember that we already have some control. Knowing if we assume that we have a quasi-randomness bound, say we know what nu in our Ramsey graph, some control already. We know that the K2A cliques are bounded. So in this case, we would understand this term when J is up between 2 and A vertices. Okay, the question is how do you use in general? And just a thing worth noting is that only look at graphs J exactly as vertices. There are at most R choose S times 2 to the S choose 2 total terms involved, basically. And so what's going to happen is we're going to need our bound to beat this contribution here. Because ultimately the problem when we expand out this large product is that the terms. And if we're just doing sort of a simple L infinity bound on each of these terms, for example, then we're going to need to beat the number of terms. So just to sort of up everything that's happened so far, we have a Ramsey graph and we have this value f. And we basically are going to tj of f above by something on the order of 2 to the s squared, where s is the number of vertices of j. And we know that the amount of quasi-random we have is that nu is around 1 over k. And here's the relation between k and r. So ultimately r, for the maximum value of s, is going to be around log k in size. So what we're really going to say is that we have a bound on tj of 2 to the negative log squared k, given quasi-randomness that is only 1 over k in quality. But don't worry, these parameter choices as they're, but sort of the moral is we have this tj and we need 2 to the negative s squared. Okay. So the sort of key bound, so this is sort of a statement that I give of the key bound that's implicit in Conlon's work. Interpret his work as one of these effective quasis bounds in and of itself is the following. So imagine that f here is a general graphon, but really you can imagine it as being the thing we care about. So supposing that unbounded and supposing that we have some j that we want to, and it contains this j vertex of degree d. Then we have this bound here. So since we all know that the K2A densities are controlled, and they're controlled quite well via this codegree bound, via the L infinity bound on the codegrees, okay, let's try to reduce our sign to graph densities to control over graphs. Upper bound this graph density by product graph densities, for example, or something of the form. And so what Conlon does, he looks at a certain local part of this J. He exploits its local structure. It's basically a van der Korpe argument. That's where this one happens. He duplicates a vertex and then he gets a clique of size k out of it while disregarding the remaining term, although that's more of a technical thing. Just recall the bound that we had for this K2D density. We get a bound of the nu to the power of du for this graph density, where d is the maximum degree of j. It's unfortunately not sufficient to bounds. Okay, so if you work an argument, then you can find that sort of this k over log k threshold is seen from some local bound on these graph densities. Okay, so we want to do better than that. We want to do better than just considering the local of this graph. And today, we want to somehow incorporate the global structure of J and get more factors of nu out, basically, in sense. We want more of these terms to show up. So we're going to make the way we do this is as follows. Here's the proposition that I proved in my favor. given a graph J, say it has SVs and no isolated vertices, then we have the following bound. So instead of a bound on the D of a single vertex, we have a bound that depends on the total. So if before we were just looking at a vertex in its neighborhood and all the other vertices, whatever, this is efficient, for example, for graphs that are, 3 regular or something. Only look for vertices in a certain sense. The idea is, okay, we better and I guess more in nature. And so, okay, so this that's not super necessary, but followed the previous short explanation. Conlon uses this van der Korpet argument on a local part of the graph. And what I do is basically I take the graph, I take a bipartition, and then I do van der Korpet twice to get rid of internal terms, and then focus resulting graph. And nice properties in terms of graph densities, because they can be written in terms of codegrees, and then you can use Holder, et cetera, et cetera. But you can sort of see that just remembering our bound on these K2D densities, this gives a bound of approximately nu to the power of, which is around f, and then over 4 for this where s is the number of J. And okay, so we also know what nu is. It's around R over K in a Ramsey graph. And okay, the R it'll be roughly negligible. Like it'll serve root K. So that this to the power of s over 4 is approximately K to the power of negative s over 4. And now here's where this log barrier comes into play. As s is at most log in size, and it's going to be what we want to be. As long as it is exponential in s, and therefore exponential in the size of the clique that we're counting. As long as that holds, then we're going to get this win. Again, there are many other technical things that go into these arguments. You have to remember the first order terms, et cetera. But this is at its core enough to give the desired win. Okay, so I'll leave it here just a second. Okay.
Sorry.
No problem. Okay. So just to summarize, one of the improvements here is really stemming from this global consideration of these signed graph densities, which sort of is translating to, as we'll pivot to in just these optimal bounds on effective quasi-randomness. And in this particular case, because of the framework had set up on this quasi-randomness and induction framework, this allows you to, in particular, as one very nice application, derive upper bounds on the Ramsey number in the diagonal regime. And I would also be very interested to see other application of these sorts of methods. I know of one thing is due to Lovaz's work on local sigma inequalities, where he does an expansion of a certain graph density and has to bound the sizes of error terms in an effective way. Although in that case, he also needs to care a bit about positivity of certain terms because he wants to prove like a local Sidorenko inequality rather than just a closeness result. But I can imagine that there are other interesting problems out there that could be handled using these sorts of frameworks. Okay. So again, we have this local bound, we have this global bound, which is sort of capturing all of the vertices in our picture. Okay. One thing that you might be unsatisfied by looking at it, if you're familiar with some of these Renko's inequality, is not homogeneous in F. So we're really using this L infinity bound on F here. And that might be a little strange. But one reason why I might think, so for example, this bound is pretty bad if F equals like 1/3. But remember, F is going to be the deviation between a random graph and the quasi-random graphon. And so F really here should be thought of as being approximately mean 0. And so it's a different beast in certain ways. So when this inequality is optimal, that actually sort of leads into the we're now going to give. So now I'm going to sort of forget about the Ramsey and just talk briefly about the ways in which this is based optimal and a reason why this roughly translates into optimal for this quasi-randomness result. So construct a graph G. So mu and u are around 1 over k in size. Yeah, I have a typo here, but so to the negative r choose 2 times this kr is far from 1. Okay, what k is less than r? So this is certainly fine. Okay, so what we're going to do is we're just focused on the case p equals 1/2 for simplicity. Find the following graphon. So the way it's defined is almost everywhere in the unit interval or in the unit square, it's equal to 1/2. And sort of the central diagonal in k different squares with dimensions 1 over k by 1 over k, we're going to bump it up from 1/2 to 1. Okay, so if you care deeply about getting a graph rather than a graphon, then you can use a standard trick, which is to sample a W random graph. So just explicitly for those who haven't seen this before, what you do is for say 1 through n, have a vertex set on 1 through n, and for I, we're going to sample a uniformly random integer or real number from 0 to 1. And then once we've sampled those xi's, we're going to include an edge ij in our graph with probability w of xi xj. So here, almost like it's a gn 1/2, but in certain cases, instead of having a gn 1/2, you just have guaranteed edges in some sense. Okay, so there are some technical computations, so I'm going to go through it in a great amount of detail, but check that mu and nu are 1 over k in size with high probability. And sufficiently large. It's 2 to the negative r choose 2 times tkr this graph, or basically for this graphon, because that's basically what it's going to be, is quite large. If n is sufficiently large, in the regime r is bigger than log k. So in the so past the regime at which the bounds I presented, there's sort of cut off some multiple of log. It's very large, and I'm not going to actually go through the calculus to justify this. So it's not too hard an exercise with these graph densities, but the reason is basically because the global bound that we had earlier is basically optimal for this of g, and therefore this value of f. Because okay, so maybe I'll just say f is here. It's going to be like k different squares of size 1 over k by 1 over. And so what's happened is all of the contribution from this graph density is going to come from all of the vertices are in the same box. Probability a to the 1 is the number of these, or depending on if connected, say, be the major contribution. The quasi-randomness is only going to remember the number of vertices here in this very extreme case. And okay, so another couple nice things is that since this w is at least 1/2, the value of f that we get is positive. So when we expand out tkr into these terms, since we know that all of these terms are positive and they're all approximately the size that the bound I give claims, you can sort of already see just it's guaranteed in some sense be roughly. But again, I won't say more about that as it's more of a technical computation. But this is sort of missing graph or graphon for these effective quasi-randomness results. Okay, so just sort of in summation, this optimality result, this effective quasi-randomness shows that sort of the standard tools of extremal graph theory that have been developed, like graph densities, graphons, graph limits, etc., looking at these graph densities and quasi-randomness trying to drive these contradictions. If you sort of forget a lot about the Ramsey graph, except for every single sort of graph density inequality that you get from these sorts of arguments, in some sense, you're going to hit a natural problem. which is sort of present to you guys today. Okay. And so just sort of as perhaps some speculation on this problem, there might be other ideas that are needed. One idea is just, or one analogy, although this is not perfect, is that it might be somewhat reminiscent of the jump from dense graph regularity, et cetera, to sparse regularity, where generally new ideas are needed. And the couple of things that you might be interested in, like for example, the global bound that I gave earlier is optimal, but the example I structured, so you might hope to maybe bring in some of the techniques from additive combinatorics and say, well, maybe if it's very structured and it's close to graph where we don't have better bounds. So if we have better bounds, maybe improvement already. And if we're near an extremal counterexample, maybe there's some way that some sort of increment or find some sort of sectors that allow you to exploit more things about the Ramsey graph. So that's one direction that might be fruitful. But I would suspect that that would only get a little bit past this log squared k at rate. Yeah, so to leave you guys with a sort of analogy, you could say that dense regularity is to sparse regularity as these effective quasi-randomness results are to what? Are there ways to push back this? Seems like once you get k, it's hard to start counting these graphs. Is there a way to characterize the behavior that occurs after this regime, even if you can't exactly like, because maybe new behavior does occur just like in sparse regularity, stuff like that. So that's sort of a very broad question, not the Ramsey problem. Certainly this is one of the most exciting problems in thanks for coming, and I guess I'll for any questions that people might have.
Great. Thank you, Ashwin. If we give him a round of applause. Thank you for a beautiful talk. So it would be great if people have got questions for Ashwin. Does anyone have any immediate questions off the top of their head? Either unmute your microphone or raise your hand or ask it in the chat. So perhaps to eat up some time while people think and phrase their questions, I can ask a kind of speculative, ill-informed question. Do these, in terms of the record lower bound for the diagonal Ramsey numbers versus the record upper bound, I don't know where people's thoughts are on which is probably the closest to the truth. Do these optimality kind of ideas, do they lead you to hedge your bets either way?
I mean, just to, sort of before a lot of the work that I've done on this problem, I was often, I'm certainly not the person who's thought the longest about this, even in this room, but sort of it always be, this GN1/2 sample feels like quite optimal in a certain sense. Yes, that's, but maybe it's somewhere in between. I always thought that morally it should be less than 4. It should be like 3 point, it should be less. But I still think that should be true, but there are ways. At the very least, I think this demonstrates, and this optimality really demonstrates that this is the problem fights back, certainly. And I think knowing that even if I could sort of characterize the things that are very close to these optimal examples that boost this, given all it would only still get very strongly sub-exponential. And so I would say it's not very clear to me, but certainly I think these looking at this malady is at least one way in which maybe people attempt to see just why we're stuck at this 4. But that's a very I'd be delighted, of course, if someone could get better than 4.
Thank you very much. Are there any more questions? Before my daughter comes into the room. Well, I certainly need to be doing other things. But if there are no more questions, I'd like to thank Ashwin for giving a talk at such a short notice and for giving such a beautiful talk at the same time. So if we thank Ashwin once more with a round of applause.